Hello everyone, welcome to this question. This question is from June 2012, which is consisting of 4.75 marks. Let us see the question. The given integral equation phi of x is equal to lambda integration from 0 to pi, that means the interval is from 0 to pi, and we have the Fredholm kind of equation kx zeta phi zeta d zeta, where lambda is the parameter and the kernel is given to be in this form, that is, it is a piecewise function, and it leads to boundary value problem. That means when you convert this integral equation, you have this kind of boundary equation where f of lambda is some known function. That means when you convert this, you will get some value of f lambda with the conditions given as phi at pi is equal to 0 and phi dash 0 is equal to 0. Then they are asking, this boundary value problem has a unique solution when f of lambda is equal to 0. When f of lambda is greater than 0, then you have infinitely many solutions. When f of lambda is less than 0, then no solution. And when lambda is greater than 1, then unique solution. Which among these four is the correct option for the given situation? So let us get started. So firstly, what we do is we convert this integral equation into the corresponding differential equation, and we'll see what is the value of f lambda. So we know how to solve, convert this. So obviously the given equation is given as the interval is from 0 to pi. So we can break this interval at some point x. So we have lambda integration from 0 to x, and then the same integration from the point x to lambda, right? And so that we may put the values of different kernels over here. So when here the variable which is over which the integration is being carried out is zeta, so here zeta is less than x and zeta is less than x over here. Therefore we'll use this value of this kernel in the first integral, and the second integral, the zeta is greater than x, therefore we'll use zeta is greater than x, therefore we'll use this value in this second interval, right? So this becomes our phi of x. Mark this as equation number 1, and now we can differentiate this using the so-called Leibniz rule. Just recall what is it. So it is this rule, right? So we can differentiate this, it becomes phi dash x lambda as such. Then this integration of this term will apply this rule, the Leibniz rule. So first term would be lambda as such integration from 0 to x, the partial derivative of this whole thing with the respect to x. That means this and this comes as such, and we only have to perform the derivative of sine x, that would be cos x. Then the next term would be the derivative of upper limit lambda as such, derivative of upper limit would be 1 as such, and then this whole term where you replace the zeta by x. So it would be cos x, sin x and phi of x. Then minus the derivative of lower limit is 0, so this whole terms become 0. The same thing we did do with this second integral. So it would be lambda as such integration from x to pi, the partial derivative of this term with respect to x, so that would be only the derivative of cos x, that would be minus sin x, and all terms as such. Then the derivative of upper limit being constant, it is 0, and everything with it becomes 0 as well, minus the derivative of this lower limit, which is 1, so lambda as such into 1 as such, right? And then this whole thing where you replace zeta by x, right? So it would be cos x, sine of x, and then phi of x. So now this term cancels with this term, and we are only left with this term and this term. So this is our equation number 2. Now this was the first derivative. We can again differentiate it using the Leibniz rule. Again we have to apply Leibniz rule twice, first on this one and second on this one. So we'll have some terms of this kind. So now if you take minus common from this term and from the third term, you'll see that this is nothing but phi of x. Just look at equation number 1. So this equation 1 is same as these two terms with the negative sign, right? And from these two terms, what you do, you take lambda common and phi x common. So you will be left with cos square x plus sine square x, and you know what is it? It is equal to 1. So we are only left with this thing. So we can simplify this. So it will be phi double dash x. We can move this to the left hand side. It would be minus lambda minus 1 phi of x is equal to 0. So you can see the given form. It is in this form only, minus of some function of lambda. So what is our function of lambda that we obtained? This is equal to lambda minus 1. Moreover, the given conditions are these, and you can verify them from our given equation also. You have phi, so let us see what is phi of pi, right? This was our phi of x. So if we substitute x is equal to pi over here, so this term from pi to pi integration, this becomes 0, right? And this would be sine of pi, and sine pi is 0, so this whole term is 0. So we have one condition, that's phi of pi is equal to 0. Second condition would be phi dash of 0 is 0. So let us look at second equation. Phi dash, when you put x is equal to 0, this term would be 0. And when you put x is equal to 0, sine of 0 is 0. So this term is also 0. Therefore we have phi dash 0 is equal to 0. So now let us look at our options. They're asking, when f of lambda is 0, then what is the situation? Do we have unique solution, infinite solution, or no solution? They're particularly asking for unique. Then they're asking if it is greater than 0, if it is less than 0, and particularly they're asking about lambda greater than 1. So let us see these cases in detail one by one. First case is that when we have f of lambda is equal to 0. So f of lambda is equal to 0. This gives me, when I put this in equation, given differential equation, it would be phi double dash x is equal to 0. So we can integrate it twice. It would be ax plus b, and its derivative would be phi dash of x would simply be a, right? So we have these two conditions. So phi of pi is equal to 0, phi dash of 0 is equal to 0. So you clearly have a is equal to 0, and you have phi of pi is equal to 0. That means you get b is equal to 0. So a is 0, b is 0, therefore phi becomes 0. And this is the only solution obtained in this case, therefore it is the unique solution. So look at our options. When f of lambda is equal to 0, we have a unique solution. So option A is correct, right? Let's look at this option. F of lambda is greater than 0. Right? F of lambda is greater than 0. Option number B. When f of lambda is greater than 0, so what was our f lambda? F lambda was lambda minus 1. We just calculated that, right? So this is also lambda greater than 1. This is option D. So we'll analyze these two cases simultaneously, right? So when f of lambda is 0, we can assume it to be some positive number, that is square of some number, and it should not be 0, otherwise we'll land up at option number A. So when f lambda is k square, our equation becomes this, and the corresponding auxiliary equation becomes m square minus k square is equal to 0, there where you replace the second derivative with m square, right? And then you calculate the value of m, and the solution corresponding to two distinct real values is something of this form: some constant into e to the power kx plus some other constant into e to the power minus kx, whatever the roots that we obtained of the auxiliary equation. So now we can take its derivative, simple, and we can apply the conditions. Phi of pi is equal to 0, this gives us this condition, and phi dash of 0 is equal to 0, this gives us a is equal to b. When you put a is equal to b into this equation, you will have something like this. So now if you have, now obviously this thing is not equal to 0. Why? Because this is only possible when k is equal to 0. But we have assumed k to be non-zero, right? So this is never 0. That means a is equal to 0. If a is equal to 0, we have b is equal to 0, and therefore we have phi of x is equal to 0 as the only solution. Therefore, we obtain one solution in this case, or unique solution. So for these two cases, we should have unique solutions. So let us look at our options. For this case, we have unique solution, so this is not the answer. For lambda greater than 1, we have a unique solution. Yes, we obtained this. So A option is correct, D option is correct. Let us see what is the case for option number C, when f of lambda is negative. When f of lambda is negative, in that case we can assume it to be minus of k square, minus of some positive number where k is not equal to 0. So our equation becomes phi double dash x plus k square phi of x is equal to 0. And the auxiliary equation becomes m square plus k square is equal to 0. So m is equal to plus minus k iota, and the solution corresponding to the imaginary roots is something like this, cos and sine. And we can take its derivative, right? No problem in that. We can apply the limits. Phi of pi is equal to 0. So sine, it would become a cos k pi plus b sin k pi. Sin k pi is 0 for every value of k. Therefore, we are only left with a cos k pi is equal to 0. And the second condition gives us phi dash of 0. That would be, this term would be 0 because sin 0 is 0. And we are only left with bk cos 0. Cos 0 is 1. So bk is equal to 0. In this case, b is equal to 0. Right? So we obtained b is equal to 0. Therefore, now the only case left is this. Either we have a as 0 or this sin k pi as equal to 0. Now if you take a to be 0, we again land up at trivial solution, and we have the unique solution as phi of x is equal to 0. But what if we have cos k pi is equal to 0? If cos k pi is equal to 0, in this case, if we assume this, we have unique solution, right? And in this case, we are saying at what values cos is 0? Cos is 0 at the odd multiples of pi by 2, right? So it would be n plus 1 by 2 into pi. So it would be k is equal to n plus 1 by 2, right? And n is plus minus 1 plus minus 2 and so on. And a in this case is arbitrary because it could assume any value. We have not attained any condition for this. Therefore, the solution would only be a into cos n plus 1 by 2 into x. Therefore, we have multiple solutions in this case because you can take any value for this a, right? So we have multiple solution for this case. So either we have unique solution or we have multiple solution in this case. And let us look at our option number C. When f of lambda is negative, we have no solution. So this is quite, you can clearly see this cannot be the case. So only correct options are A and D. Thank you for watching the question.